Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 3 on linear modeling. So we've already looked at linear change and we've looked at how to represent linear functions with both the point-slope form of a line and the slope-intercept form of a line. We're going to combine both of those ideas today when we do more modeling of real-world problems using linear functions. So let's get into it right now. All right, here we go. Modeling constant rate of change. Due to their simplicity, linear functions are used to model a variety of real-world situations, especially those that have a constant rate of change, right? Constant rate of change means linear functions. Let's take a look at exercise number 1. David was driving away from New York City at a constant speed of 58 miles per hour. He started 45 miles away. Letter A. Write a linear function that gives David's distance d from New York City as a function of the number of hours h he has been driving. All right, pause the video now and see if you can write down this linear function. It should be relatively simple. All right, well, let me use a highlighter really quickly because to me, this is really important, right? Here we've got this idea that we've got a rate, 58 miles per hour, and that's going to be our slope. A starting value, he started 45 miles away, and that is going to be our y-intercept. Well, let's try that again. There we go, right? So if you see a rate, right, what we've got up here, 58 miles per hour, and a starting value, 45 miles away, then we've got both our m and our b. So if we're thinking about kind of like y equals mx plus b, I'm going to put it in terms of d. We've got our m, we've got our b. So my distance is going to be 58 miles per hour times how many hours I've driven, plus that 45 miles that I started away. All right, let's take a look at letter B. David's destination is 270 miles away from New York City. Algebraically determine, to the nearest tenth of an hour, how long it will take David to reach his destination. All right, well, see if you can do this. Pause the video now and see if you can find out to the nearest tenth of an hour how long it's going to take David. All right, well, David's destination is 270 miles away. That means that we want to solve the equation 270 equals 58 times h plus 45. So this is a simple sort of two-step equation that you would have been solving back in, I guess 7th grade math. We just need to subtract 45 from both sides. That's going to give us 225 is equal to 58 times h. We'll divide both sides by 58, and that's a little bit of a messy calculation, but that then gives us that h is going to be, to the nearest tenth, 3.9 hours. To the nearest tenth of an hour. All right. Now let's take a look at letter C. What might affect the accuracy of the prediction that your model made in part B? Well, see if you can write down one or two things that would affect how accurate that 3.9 hours is in terms of the estimate of when David will reach his destination. Well, there's a lot of different things, right? One of the things might be, if I can scroll down, how constant, and this is probably the biggest thing, how constant David's speed is, right? And that kind of boils down to some of the other ones, maybe how accurate the 270 miles is. Maybe it's actually a little bit more than 270. Maybe it's a little bit less than 270. Does David take any stops? Or does David make any stops? And that probably kind of really loops back into number one, how constant David's speed is, right? But there's a lot of things that are, of course, going to modify that accuracy. These days, right, we put a destination into a GPS, and I'm always amazed, right? I'm always amazed at how accurate it is in predicting the time that I reach my particular destination. But at the same time, and it's doing a lot of this kind of mathematical modeling in the background, right? But at the same time, all of a sudden an accident occurs, right, on the interstate, and suddenly I go from, being in the blue on the way up to being in the red, come to a complete and utter stop, and now whatever that 3.9 hours is has suddenly become 5.1 hours, which is horrible. All right, let's keep moving on. But it's always important, right? When we use mathematical models to make a prediction about something, there's always some inaccuracies in those models, and we want to be able to think about various factors that can affect the accuracy of our predictions. Now, when a constant rate, which is a slope, and a starting value, a y-intercept, are given in a situation, like in the last problem, linear modeling is relatively easy. Sometimes we are given two input-output pairs and have to construct the model from them. And we've already done this in the last two lessons, but let's do it a little bit more in this particular exercise. Exercise number 2. Maeve is trying to model her cell phone plan. She knows that it has a fixed cost per month, along with a charge per call she makes. In her first bill, Maeve made 34 calls and was charged $10.85. In her second month, she made 52 calls and was charged $13.55. Letter A. Create a linear model for the amount Maeve must pay per month, P, as a function of the number of calls she makes, N. Write in slope-intercept form. All right. So this is very similar to what we did in the last lesson. Let's start together by laying out two coordinate pairs that are really given in this problem. Then I'm going to have you work on the linear model on your own. So let's do this first, right? So we know that we've got the point 34, 10.85, and we've got the point 52, 13.55. And although this is a little bit messy, right, we've got those 2 points, so we should be able to calculate the slope. And what I would then suggest is writing the model first in point-slope form and then algebraically manipulating it in order to get our slope-intercept form. Pause the video now and see if you can come up with that linear model. Now, if you're most comfortable first writing the model in terms of x's and y's and then translating it in terms of p and n, that's fine. There's nothing wrong with that. But let's take a look at how we develop this model. Let's take a look. All right, so to begin with, let's calculate the slope. Now, my slope is going to be the change in my price over the change in the number of calls. So I'm going to do 13.55 minus 10.85 all divided by 52 minus 34. Now what's great is you can actually just put that totally into your calculator right from the get-go, and what you'll find is that's 0.15, just perfectly nice like that. Now what I can do is I can use that slope, let's say, and maybe, I don't know, I'll go with the first point, this thing, and I'm going to write in point-slope form. I'm going to say p minus 10.85 is equal to 0.15 times n minus 34. Okay, now we looked at this sort of earlier in a different lesson, but I can now distribute the 0.15, right? So this is my nice point slope form. Gives me p minus 10.85 minus, equals 0.15 n minus 5.1. That's what I get when I do 34 times 0.15. I can now add that 10.85 to both sides, and I'll get p equals 0.15n plus 5.75. And I'm sorry, I kind of barely got that model in there. Maybe I can actually just unlock this a little bit, drag it down, give myself a little bit more room, and then we'll lock that right back up. All right, so it doesn't move around on us. All right, so we've got our final model, which I then can't untangle. There it is. So, and again, keep in mind what I did, right? I first calculated the slope of my model, 0.15. I then used the point slope form of the equation right here to kind of write an initial model. I then distributed the slope through the right-hand side of the equation and then rearranged so that I got my final slope-intercept form. So the amount that Maeve pays is 0.15 times the number of calls she makes plus 5.75. Now let's take a look at letter B. Interpret both the slope and the y-intercept of the model you created in A. All right, what I'd like you to do is pause the video now and interpret what the 0.15 tells you and what the 5.75 tells you. All right, well, here we go. The slope is always a rate, right? And it's the change in this compared to the change in this, the change in the price compared to the change in the number of calls, which means it has units of dollars per call. So 0.15 tells us that it costs $0.15 per call. The 5.57 tells us that the fixed cost is $5.75. All right, in other words, if Maeve makes no calls whatsoever, she still is charged $5.75, right? But for every extra call that she makes, or for every call she makes, she's then going to have to pay 15 cents or $0.15 per call. Okay, let's take a look at letter C. Maeve's friend Serena has a cell phone plan that charges 8 cents per call and a fixed monthly cost of $10. Determine the number of calls that it would determine the number of calls that would cause the two monthly charges to be as close as possible. What is the difference between the two costs for this number of calls? All right, well, see if you can first model Serena's sort of call structure, and then see if you can set up an equation and solve it to find the number of calls that makes their two monthly costs as close as possible. Pause the video now and see if you can get through letter C on your own. All right, well, first let's lay out Serena's. Now, Serena's plan is much easier to lay out than Maeve's because we already know that she's being charged 8 cents per call, and we also know that she has a fixed monthly cost of $10. So let me just kind of lay out Serena's. All right, so Serena's plan, right, that's P equals 0.08 n plus 10. If we want to find out what's going to make them cost as close as possible, then what I'm going to do is I'm going to take Maeve's cost, 0.15 n plus 575, set it equal to Serena's 0.08 n plus 10, and now I'm just going to solve that equation. And this is a little bit more messy because we're involving decimals and things like that, but it's okay. I just subtract 0.08 n from both sides. All right, that's going to leave me with 0.07 n plus 575 is equal to 10. All right, now we'll subtract 575 from both sides. Maybe do a little extend the page to give myself some more room. That's going to be 0.07 n is equal to 425. And now I'll divide both sides by 0.07. All right, and rounded to the nearest whole number, that ends up being 61. All right, now it's a decimal, all right, but rounded to the nearest whole number, it's 61. Okay, so the question then becomes, what is the difference in the cell phone plans at that point, right? If it was exactly 61, right, we didn't just round there, then of course the difference between the two plans would be 0, all right? But we can now use the 61 to figure out the cost of both plans and how different they are at that point. So let's do that really quickly as well. All right, so we know that we've got 61. So for Serena, right, we've got P equals 0.08 times 61 plus 10. And that is going to be, what, 1488. And for Maeve, let's see if I can spell hers right. P equals 0.15 times 61 plus 575. So for Maeve, we've got 1490. And notice how very close those two are, right? You know, Serena's at $14.88, Maeve is at $14.90, right? They're not equal because this thing is a rounded version because we can't have a decimal number of phone calls. And so the difference, which I think we can do in our head, is 0.02. When they both make 61 calls, there's just a 2-penny difference between their plans. All right, so a little linear modeling, right? And it's interesting because in some cases with linear modeling, like with Maeve's cell phone plan, we had 2 input-output pairs, so we had to generate the slope. We had to do some work to find the y-intercept. On the other hand, with Serena's plan, we knew the cost per call plus the fixed cost. All right, so we were able to immediately know the slope and the y-intercept. Let's do a little bit more with linear modeling. Working with linear models. Sometimes a linear model is given to us, and we want to interpret it or use it in some way. Models in the real world can be messy, and we even saw that in the last example, and it's often convenient to use our graphing calculators to plot and investigate their behavior. So we're going to definitely use our graphing calculator on this one. Make sure that you've got something that can graph and find intersections and things like that. Let's take a look at exercise number 3. A factory produces widgets, which are generic objects of no particular use. The daily cost, C, in dollars to produce W widgets is given by the equation C equals 0.18W plus 20.64. So that's kind of a model similar to what we were just seeing in the last problem. Each widget sells for 26 cents. Thus, the revenue gained, R, from selling these widgets is given by R equals 0.26W. Letter A. Use your graphing calculator to sketch and label each of these linear functions on the interval 0 is less than or equal to W, which is less than or equal to 500. Label your lines and your y-axis with its scale. All right, cool. So what I'd like you to do is actually get that graphing calculator out. I'd like you to experiment. Put both of these in at the same time. Maybe C goes into F1 and R goes into F2. We know that we're going to want our X window to go from 0 to 500, which is quite large. We don't quite know yet what our Y window should be under, although you could take that 500 and you could plug it into either one of these things to try to figure out sort of what your largest Y value is going to be. But what I'd like you to do is play around with this right now and see if you can get a good picture on your graphing calculator that has both of these linear functions on it and a good Y window. Take a few minutes to explore this right now. All right, well, let's play around with it. And as I said, one thing that might make sense right away is to just ask ourselves or to play around with, figuring out what that window should be. Now I'm going to put the two functions in. I think I'm going to put the cost function in as F1. So I'm going to put 0.18x plus 20.64. All right, and F2 is just 0.26 times x. Now right now, of course, when I look at this, I don't see anything that even remarkably looks correct because I have just my standard graphing window. All right, so what do I need, right? I really need, at this point, to play around with my window. Now, one thing I'm going to do is I'm definitely going to just go in and I'm going to change that to 0, and I'm going to change this to 500. But if I do that, of course, you know, without changing my Y window, I don't see anything that looks good, okay? Now, I could kind of just play around with it, and in fact, let's do that. Let me go into my menu, let me go back into my window settings. I know I've got my X window correct. I'm not going to worry about my scales. I'm going to do my Y minimum is 0, and maybe my Y maximum, I don't know, let me do 200. All right, and that definitely looks a lot better, right? In fact, it might just look perfectly fine. You know, there is some space up here that seems like, you know, I don't really need. So maybe I'll go back into my window one more time, because I like getting a good window. That's just me. Go all the way down here and maybe set that at 150. Maybe that'll look a little bit better. Yeah, I like it, right? Good graph. Perfectly good, right? I can really see the behavior of these two things. The red one is my revenue. The blue one is my cost. And again, you could get a good sense for that Y window by literally taking these two functions, both of which are increasing linear functions because they have positive slopes, and just putting in the 500, right? Put in the 500 in both of these and you'll know what the maximum Y value is at that point. All right, that being said though, let's do a little sketch. Maybe I'll put, just like this, I'll put my C of X. What was my window? It was like 150 here. I think I'll just kind of stick with the same colors. And R of X, like that. Okay. And maybe I would want to label them with my equations or something like that. Maybe I should have had them a little bit less steep. But that's good enough for my purposes right now. Let's take a look at letter B. Use your calculator's intersect command to determine the number of widgets W that must be produced for the revenue to equal the cost, right? So I want to know where the revenue and the cost are equal, so I'm going to use the intersect command to find that location. Pause the video now and see if you can remember how to do that, and then we'll go through that on our TI Inspire. All right, here we go. Let's bring up the Inspire. We're going to go into menu. I'm going to go into number 6, which is analyze the graph. For me, one of the most important things is intersection. All right, I just need to move that sort of dashed line to the left of my intersection. I'm going to hit enter. Then I move the line to the right of the intersection. I'm going to hit enter. Then maybe I'll move this point up like that so that we can actually see it. And there it is, right? So we have our intersection at 258, 67.08. So 258 and 67.08. Let me just make sure that's right. And I wish the little hand would get off of there. Yep, there we go, 258 and 67.08. Which means, right, if we produce 258 widgets, right, then what will happen is that the cost of producing them will be $67.08, and the revenue we generate from selling them will be $67.08. Awesome. Okay. Now maybe we'll go back. We'll be going right back to the calculator in a second, but let's go back full screen and let's take a look at letter C. Profit is defined as the revenue minus the cost. Create an equation in terms of W for the profit P. All right, why don't you go ahead and pause the video now and go ahead and do that. All right, well, let's take a look. I'm going to switch back to blue for a moment. All right, and what do we know? We are told that profit, right, in terms of widgets, is equal to my revenue minus my cost. So my profit, in terms of the number of widgets, is going to be 0.26W minus, and I want to be careful here because my cost is a little bit more complicated, W plus 20.64. I need to distribute that subtraction. I'm going to try to move this down just a little bit so I give myself a little bit more space. There we go. And lock it back up, hopefully. There we are. So I need to distribute that subtraction. 0.26W minus 0.18W minus 20.64. And finally, right, when I combine like terms, what we'll have is that my profit is 0.08W minus 20.64. Red wants to come out no matter what. There we go. Beautiful. All right, so there's my profit. And it makes sense, right? Like profit is whatever money you brought in minus whatever money you laid out. Your revenue is the money you bring in. Your cost is the money you lay out. Your profit is the difference between the two, specifically revenue minus cost. Little economics. All right, letter D. Using your graphing calculator, sketch a graph of the profit over the interval 0 less than or equal to W less than or equal to 1,000. State the X and Y intercepts of this line and label them on the graph. All right, so we need a brand new graph now. I'd like you to pause the video. You might want to clear out the other two functions because you're going to put this new function in and your window's going to change. Now instead of going from 0 to 500, I want to go from 0 to 1,000. And we can certainly have negative profit, which is why we've got sort of both sides of the y-axis right here. Pause the video now and see if you can come up with a reasonable graph for what the profit looks like when the widgets go from 0 all the way up to 1,000. Take a little bit of time now. All right, well, let's take a look. Again, I've kind of got to exit out of this thing. I think I'm going to go in here and just open up a brand new document. That way I can just do a brand new graph. Here we go. So I've got to figure out somehow how to get this thing in there, and we'll just do it like this. So I've got 0.08x minus 20.64. All right, we got to play the window game again. Now here, my window is going to go from 0 to 1,000. And now I've got to have some negative and positive. Maybe I'll go negative 100 to 100. And we actually don't get the worst graph there. That's not terrible. Now, I probably have a little bit more down here than I need to, especially given that my y-intercept, which is easy enough to think about because it's negative 20.64, is well below that negative 100 that I set. Up here, the window's a little bit better, but it's still probably more than I need to. So I'm gonna try to make this take up a little bit more space. I'm gonna go in my window settings, maybe I'll go negative 50, and just to keep it symmetric, 50. And then of course that upper one wasn't quite what I wanted, maybe 75. Ah, I like that. Look at that. I always like it when a curve takes up more or less the entire window, right? There's not much wasted down here or up here. So I've got negative 50 down here, 75 up there. Let's get that sketch really quick. Right, so maybe negative 50 down here, 75 up here, and we've got a graph that looks something like this. Now, it also said for us to label the y-intercept and the x-intercept. The y-intercept we already know. That's negative 20.64. If we really needed to, we could go into a table and look at it, but we should know what the y-intercept is. Now the x-intercept, right, another name for that is the 0. Let's find that really quickly on our calculator. All right, so let's go menu, analyze the graph. Let's find a 0, okay? So I'm gonna 0 is just another name for the x-intercept, so I'm going to hit enter. Here, enter. And my my x-intercept is at 258. That number should sound kind of familiar. All right, and it should sound familiar because that is exactly the number that we had here. Remember, profit is revenue minus cost. We found out where the revenue and the cost were equal right up here, and so that point, 258, becomes the 0 of this function where we've subtracted those two. So obviously if they're equal, right, the revenue and the cost, then what's going to happen is when we subtract them, they're going to give us a 0. All right, let's take a look at one last piece, letter E. What is the minimum number of widgets that must be sold for the profit to reach at least $40? Illustrate this on your graph. Now, we could certainly do this algebraically, right? So we should feel very, very comfortable with taking this and setting it equal to 40. In fact, let's actually write that down real quick. We want to solve 0.08w minus 20.64 is equal to 40. And we have easily the algebraic ability of solving this. We could have solved this probably back in 7th grade, certainly 8th grade, algebraically. But let's do it graphically, all right? Pause the video now and see if you can solve this equation using your graph as opposed to algebra. All right, well remember, to solve something graphically, what we kind of want, right, is we want this one in f1 of x, and we'll put this one in f2 of x, and we'll find out where they intersect. So I'm going to go into menu, graph function, f2 of x. I'm going to have my constant function. There it is, right? So there's my 40. Now I'm going to use my intersect command, menu, analyze graph, intersection. I'm already to the left, so that's good enough. Bring it to the right. And it looks like 758. 758 comma 40. Let's kind of get all of that on our graph. Let me go back to here. So I'm going to graph y equals 40. Put my point down. I'm going to have 758 comma 40. I'll label this graph my profit as a function of my widgets. And therefore, the minimum number of widgets that would have to be sold in order to make a profit of $40 is 758. Make sure, did I say? Yeah, 758. And again, that is exactly what we would get if we took this equation, added 20.64 to both sides, and then divided by both sides by 0.08. But it's kind of nice to remind ourselves that, of course, equations can be solved both algebraically by going through our algebraic manipulations, or can be solved graphically by graphing the left side, the right side, and finding an intersection point. All right, let's wrap this up. Linear modeling is exceptionally important. It's important in science, mathematics, economics, a whole variety of fields. And it's important because linear models are simple. They're easy to use, they're easy to graph, they're easy to manipulate algebraically, and they're easy to come up with if you've got a lot of important information. Now there's of course, many phenomena in the real world that don't lie along a straight line. Okay, many things, right? But if we know that something can be modeled with a linear function, then they're easy to use. Or if we don't have a sense for what proper function should model something, then linear is often our first attempt to work with because they are so simple and, right, they're easy to explain to outside people, right? We don't have to be like, well, I fit this with a cubic function or with a semi-logarithmic function or something like that, whatever a semi-logarithmic function is. All right, so we'll work more with linear functions, obviously, throughout this course. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.